Hello, we are Team 23, Arif, Megan, Chandler, Maureen, and Gustavo, and this is our analysis and redesign of a smoothie maker. Our chosen product is the Kenwood 2B200 Smoothie Blender, which mixes liquids and soft foods together. Its key features are a dispensary tap, 3 different blending speeds, and non-slip feet. The estimated production rate is 250,000 per year. Here's an exploded view with key subassemblies highlighted. The primary customer group consists of home cooks such as single adults or parents with children. They require a simple interface, convenient sizing, and extra safety features for children. The secondary customer group is composed of professional chefs and baristas who want a blender that can withstand high usage, high power requirements, and quick cleaning. Here's the fast diagram for our chosen product. The smoothie maker's main function is to combine ingredients. The 2 main functions that offshoot from this include mix contents and store contents. Here you can see the top-down assembly sequence, which begins at the container and ends with the lid. Similarly, here is the bottom-up assembly sequence, which starts at the main body and concludes with the container, which includes the tap subassemblies and the lid. The assembly sequence analysis shows that the bottom-up sequence is the better assembly sequence. The bottom-up sequence is notably more preferred for ease of transferring and handling and ease of testing subassemblies. This top diagram is the assembly sequence diagram for the bottom-up assembly. Below that is the diagram for delayed differentiation, where the assembly process diverges much later after all the components, except for the lid, do not differ between customer groups. The function component mapping matrix illustrates the relationship between the parts of the blender and the key functions they serve to accomplish. The functional differentiation table organizes the functions from the fast diagram into 2 categories based on their application to the 2 customer groups. Assist pouring and control speed are the functions that differ between the 2 customer groups. Components listed on the left are platforms and are shared between variants, while the speed setting buttons, container, and tap assembly are components that are different between the primary and secondary customer groups. The variants that address handling liquid removal are the tap feature for primary customer group and the spouted pour for the secondary customer group. The container handling variants are the dispensary tap for the primary customer and the inclusion of a plastic handle for the secondary customer to accommodate the use of ergonomics. The main body variants are the inclusion of a power dial for the primary customer and the option of power buttons for the secondary customer group. Here's the bill of materials and quad chart classification for the smoothie blender. And here are some assumptions our team used to create the bill of materials.
Design for manual assembly. So first thing we did was we created the manual assembly time, and by looking at that chart and the quad chart, we saw that we can redesign the tap rod and the bottom tray. For the tray, that is our platform part, and for the redesign, we added ribs on the inside for DFA A8 to prevent nesting, and on the rim we added notches, which is DFA 10 for easier insertion to the main body. We also reduced the number of buttons or rubber feet for underneath the tray, for it was 5 and now it's 3. And for the tap rod, that is our module where we have both the tap rod and the stopper. And for the redesign, we're able to combine them and reduce the number of parts needed for DFA 1. We also changed the nod feature for DFA 10 to make it easier to insert to the tap button. We also have the chamfer underneath where it adds the feature of easier to insertion. And also in this design, for DFA 13, it avoids readjustments between the 2. So in the post manual assembly time, we can see that we were able to reduce the time by roughly 21 seconds, which greatly impacts production in a positive direction. Design for automated assembly. So the subassembly we chose was the blade subassembly because there are plenty of small parts we can use. And doing the pre-automated assembly cost, it's roughly 27 cents per assembly. And within the subassembly, we chose the blade rod with the rivet on top, the connector, and the top and bottom blade to redesign. So for the connector, we were able to combine the thin, thick metal rubber rings in the cone connector, which greatly reduces the number of parts. We also have a shafter on there, which helps avoid readjustments to the connector. and we added a chamfer through the hole to make it easier to insert. For the blade, we're able to combine the top and bottom blade, reducing the number of parts. We're able to increase part symmetry with having them combined and can be inserted in any of the beta directions. And the threads inside helps facilitate orientation. So for the blade rod, a picture without the rivet, having threads on both sides helps increase part symmetry, makes it easier to insert. With the threads, it helps facilitate orientation. With this helps minimize the rod turning over to insert other components, since now everything can be inserted from above in the Z direction. Post-assembly cost, we were able to reduce the assembly cost to 18 cents.
Moving on to the process selection, we have chosen the blades from the blade assembly in the bottom tray. Here we have a 2D view highlighting key geometries that guide the selection. Given the dimensions of the blade, the two options for manufacturing process are machining and sheet metal working. Taking into consideration the functional mapping matrix, the blades are most importantly cutting the contents and transmitting a torque, which requires a high modulus of rigidity, preventing the blades from breaking. Additionally, the material of the blade shouldn't be prone to oxidation or corrosion given how it is interacting with food. Conventional machining is able to provide the sharp shape of the blade while ensuring the material's integrity and rigidity when machining. Given the key dimensional components of the tray, the two options for manufacturing process are machining and injection molding. Taking into consideration the functional mapping matrix, the tray is most importantly facilitating cleaning, which requires a quick and easy way to detach and reattach again. Injection molding the redesigned tray will allow for easy access and alignment with the slots to snap into place. Additionally, the material of the tray should be non-porous to aid with easy cleaning and preventing odor. Injection molding will allow for the part to have a consistent wall thickness and the unique shape to accommodate the redesigns and maintain its function of facilitating cleaning.
Given the processes and parameters mentioned previously, we put our selected parts, the tray and blades, through our DfM software in order to improve them for our redesigns. Looking at the results for both parts selected, we took into consideration focusing on the high priority recommendations. First, for the tray, the immediate issues identified suggested taking a look at existing rib parameters, draft angles, and wall thickness. Addressing these issues, we changed the rib thickness to prevent nesting issues and match existing part thickness, increasing draft angles for the feet at the bottom, and fully fill in the volume of under the ribs to be fully connected to the whole part, removing undercuts. Looking at the blades, the higher priority recommendation suggested looking at standardizing hole sizes, removing any partial holes, and eliminating sharp internal corners and non-uniform draft features. Addressing these, we adjusted hole size and fixed the threading to be more standard and generally smooth and filleted various edges to avoid unnecessary sharp edges where not needed for cutting. Looking at our cost estimations, by making these changes, we lower manufacturing costs on the tray by about 14 cents and the blades by about 18 cents. Additionally, by using online resources to estimate for our proposed production rate, for a blades batch size of 250,000, our post-DfM costs are decreased by about 4 cents when compared to our costs of the pre-DfM analyzed parts.
Now we'll go over the design for product service system. A product service that could be offered to both primary and secondary customers could be blade replacements and customized blade tips or attachments. This would allow customers who already own a blender to replace out their dull or worn out blades for a new sharper one, or just choose a custom blade for the specific needs. This would improve customer experience because it allowed customers to keep their blender for a longer period of time, but retaining the high quality by changing out the blade. And the environmental benefits is that it increases the product shelf life by allowing the customer to keep the blender for long periods of time by just replacing the parts that are broken. This would cause less amount of units being produced and thus less resources being wasted. For conclusions, we noticed that for our redesign, we have cost reductions from automation 9 cents per part, and for manufacturing 31 cents per part. For our overall product redesign, a pro we noticed is that we reduce the number of small parts in the blade assembly, overall increasing the efficiency of its assembly and cost. A con could be that we don't know the full impacts of removing all these parts for long term, but we could do prototype testing to test this out. Our product analysis, if we were to do this again, we consider redesigning the container or tab. That could be as equally interesting for the project redesign, or just considering a new shape for the container.